Now we will measure an FRF of this pan, a frequency response function of this object. And as we learned in the 3 videos before, the easiest way to get the FRF is to put an impact on it. So I just put an impact on the pan. And the response is boom. There's several tones in there. It's easier to hear if I impact it here. Boom. So some tones are in there, and that is the eigenvalue, the eigenfrequency, the modes in this pan. And that's what we want to see. But as we hear, I can hear the tone. And that's different to the example I showed in the previous videos, where it's just a mass about 1 or 2 hertz. Now it's about 300, 400 hertz, because the masses are very small and the stiffness is much higher than the spring. So the swinging motion of the pan is very tiny and very fast, so I can't see it with my eyes. So we need measurement equipment. For the stimulation, for the input, we use an impulse hammer. Let's listen up. Really high frequency also now stimulated by this device, and it measures the force, how force gets in. For the output, force is equation mass by acceleration. We use an accelerometer, really small, tiny symbol, doesn't have a lot of mass, so there's no change on the object, and we can glue it on our test object. So our FRF is now the relation between the output, as we learned before, now in meter per second squared, divided by the input. Now this is force. And this relation between amplitude and phase will be the FRF from this point to this point through the pan. To acquire now these fast changing data, we need an acquisition system, a front end. Now we have only 2 channels, input and output, so there's this tiny one here, it's completely sufficient. So let's connect. Okay, switch it on. The hammer goes on that channel and the accelerometer on this. Okay, and now this data is collected, even this high sampling rate, via USB to a laptop. There, an acquisition software, especially for impulse measurement, is already set up. This is the Ultimate Suite software. It's a very handy one because it automatically reads out the right sensitivities from the connected sensor, easy, and it sets the right parameter for the transfer function calculation, block size, sampling rate, pre-trigger, threshold, Henning windowing. Difficult in the beginning, it's complex. That's why I made an extra video tutorial just about this topic. But if you just leave it on auto, it will be set perfectly for the object you strike today. That's why I like it. Furthermore, it tells me where to place a reference sensor for optimal result and tells me where to strike the object. So for beginners, this is a good start point. So it tells me the reference point should be placed in that spot and I should impact with my hammer at this side. Let's see. And there it is. So this is our amplitudes, and we see a lot of degree of freedom. So we had a lot of modes in there, and below we see the phase. Let's see this a little bit bigger here. Maximize. So here are the amplitude that rises at certain frequencies, and we see the phase below could be 0, it would be in here. At a certain frequency, it's 180 or minus 180. It flips over from 180 to 0 again, depending on the frequency. So low damping at this point, good result. So we're done now. No, I hit it here, maybe there, maybe there. There could be a small deviation in the way where I hit it. Maybe the angle is not perfectly. So you should measure the same point several times and compare if we have constant results. That's why here is strike 1 of 3 suggested by the software. So I make 2 more. Same point. Except that means it is the same. So go on. And then now we have an FRF measured. We have a good idea how many eigenfrequencies are in this pan and where they are. But we cannot see them yet. I like to see how it's moved, what's happening at maybe 600 Hertz. And that's why it's quite clever to measure different FRFs from different points, always to the same reference, and then see the amplitude will change and the phase deviation will also change over to the same reference point. And then we have an overall picture of what's happening in the pan at a certain frequency. So we just go on. So the next point will be at this point here. So I make a small dot in here, easier to mind. Keep it calm. 1, 2, 3, done. And like this. So the next point will be just at the bottom. Whoop. If I do this wrong, he automatically rejects it. That makes it so handy. So we've done with the measurements. Now let's have a look at our transfer function and what does it mean to our pan. So we take all the frequency response tracking that we acquired and put it in viewer. So here we see the transfer function amplitude and the transfer function phase. And now we can just scroll to all the measured FRFs and you see transfer functions look different depending on which point we look at to the reference. So it's not that easy to have an overview. One option for you to have an envelope. It gives you always the highest peak of all transfer functions, but you don't know where you are. I like this viewer below. It shows all the transfer function in one glance. Every line is one transfer function. When the peak is high, there will be a high color. So I can see in just one view at low frequency, only a few parts have some amplitude. So maybe I just go there, okay, and press play. And here I see, yes, only the left parts here. The handle is moving with what is about 20 Hertz, okay? Not that interested here. So I can just pick the cursor again and move it maybe to the next interesting frequency. Still a very full body mode, not at low frequency. So we go to the next frequency. I can see here is a lot of motion at other parts of the pan. And yes, so what we see here is the amplitude and the phase relation of all measured FRF animated on the object we measured. It makes it so handy to have a complete overview of what's happening at my pan. So I like to have this mode shape, we call it, and just press plus, okay? And there we got it. It's a measured shape, 345 Hertz. I can press play, but where's the damping? I want to have the damping. Some people go to the FRF and try to get the damping from that form shape. I strongly say do not do this. It's more an academic idea to see with sigma 3dB. The shape of the FRF depends on the sampling rate and the block size you've chosen before. So depending on your frequency setup, you get different frequency dampings. Not right, this stay constant, okay? Another thing is you only pick out one FRF, one point, the damping at one spot, but you should have everything included. But the worst thing is there could be several modes at the same frequency. Look at this area here, for example. If I just go with the cursor in there and animate all the modes, you can see, okay, there are these diagonal movement of the edge and just very close to the same frequency, almost the same movement, just 45-degree tilted. So it's almost the same. And we have a lot of these points, especially when they have this symmetrical object like the pan. If you look at all the FRFs, it's easy to miss one of the F3 at once. So easy to miss and to make an error on the mode detection and on the damping. If you want to have a damping, there's one simple trick. You have to do a modal analysis. Oh my God, how is this done? Show you how. You take your hand, go to your mouse, and then go on this button and say calculate poles, and you have done a modal analysis. No pre-knowledge needed, because in this software there's an artificial intelligence side, looks at all the specs, look at all the coherence that we have done in the measurement before, and set up the right algorithm with the right parameters so we have a perfect result. And there we are. Just leave it here on automatic and you're safe, you do it everything right. Now we have done a modal analysis based on our FRF transfer functions of this pan, and all we have to do is just give me all modes. And second click I have to do, and now we have it in a list. I can sort it maybe by the frequency, what should be on top, maybe the lowest on top, and just click on it and see, oh, this is high damping, 4, it's a relative value, it's in percentage, and press play. And I see, yes, it's the handle, it's a very long thing, and it can move at very low frequency, and it's made of plastic. That's why I have this high damping. We understand this now. Next one is also quite high damping. Still the handle, a lot of movement. Let's go for something with low damping, and maybe this one here. Oh, this is completely different. 63 Hertz. Yeah, that's what we probably expected. There's a big motion here of this full metal plate pumping up and down, and of course this can swing a long time. Yeah. Let's check now this frequency region where these close symmetric modes are. So this is 281. Yeah, this is a clear, we call it second order circular mode. Yeah, one time around. And really close together is with that one, which looks different, yes. And only 20 Hz higher, 3400, is this one, which is almost the same, also second mode circular, but now accompanied by a mode shape, also second order in the beam of the handle, which is plastic. That's why it has a higher damping than this one, okay? Everything is logic, but it's important to separate these close modes. Let's check this in close here. This is the region. Here's this 1, 2, and 3, very close together. And depending on the FRF you just pick to look at, yeah, it's completely sometimes weird to see these modes in just one FRF. No? And if you think about getting a mode like this with the simple idea of having a Sigma 3dB, you miss that, okay? And all you gotta do is just 2 clicks. Calculate the pulse, give me a list, and the artificial intelligence gives you a list of all the stable poles of your object. Now you can export it and compare it with simulation data or with other measurements or other pans. Now we have a clear and good result. So if you want to learn more about impact testing and all the settings that have to be in there, and especially model analysis and how this has been done, there are several tutorials I already made and will make about model analysis in total. So just follow the playlist in YouTube and you get a perfectly overview. See you there.